Today we're going to install a train line in a construction depot, breaking down the engineering and costs. I'm Daniel and this is Ashville. Setting up your own train line sounds like an astronomical task, because it is, but it's not impossible. We are the Ashville group of companies. We specialize in aggregates, concrete, waste management, plant hire and construction. Since 2019, the business's main source of material, which is construction aggregates, has been delivered by rail. In December of 2023, Ashville secured a new home in a rail yard with a 50-year lease. However, it had been unused for many years and the track was unusable. So today, we're gonna plan and install a new train line. This is our old yard, and this is our new one. Firstly, we need to work out what it is we need from this train line, which is, the train line needs to be as long as possible to help us with economies of scale and reducing our carbon footprint. But we need this on the smallest footprint possible because the yard is only 5 acres and we need every inch of it for daily operations. We need to be able to maneuver within our yard because the train arrives locomotive first and needs to leave locomotive first. Now the setup in our old yard was that we had to drive past, go down to a third party, turn around, drive past the yard again and reverse in. Now, while it is possible, you need to pay the third party for the privilege, and we would prefer to be masters of our own destiny. We need to be able to keep it clean. So a good old conventional track ballast finish is not ideal. And we want to use as much of the old track as possible because we like to do our part for the environment and it will save on costs. Starting to work out the layout, this is going to be governed by where the site is connected to the main network. We have 2 connections, one at the top and one at the midway point, both on this side. The previous layout crossed over into the middle of the site. Now that's not going to work for us because in my personal opinion, that is not effective use of space. So we are going to hug this fence line. Our old yard was able to accept 24 wagons and was just under 400 linear meters of rail. Now in the new yard, we would like to accept 26 wagons, so we're gonna need roughly 450 meters. To make use of the 2 connections, we're gonna have a secondary line, which means the train can arrive locomotive first, uncouple, switch on to the secondary line, back out on the main line, reconnect and push the train in. When it's ready to leave, it will already be facing the right way. We're going to be offloading material from the train and loading waste onto it. Now, while our team are well versed and very good at this, a little bit of spillage is unavoidable. And we need to find a way to keep this clean. We have a road sweeper, which we use to clean the loading and general areas within the yard. This would be ideal to use to clean the train line, but we're going to need a surface which makes this possible, like concrete. At this point, a structural engineer steps in to calculate the load and stress which will be placed on the train line. Each train will weigh almost 3,000 tons. The locomotive itself is roughly 130 tons, and each of the 26 wagons will weigh 100 tons. That's 25 tons empty with 75 tons of material in each one. The build-up beneath and the support within the concrete needs to be strong enough to support this weight or it will crack and break away immediately. And the concrete needs to be 50 mil lower than the top of the rail on the inside so it doesn't obstruct the wheels. Lastly, the track has been inspected. While it's not pretty and in need of TLC, it has been confirmed it can be reused. And we have a number of concrete sleepers that we can also reuse. The B stops are also not very pretty, but perfectly operational and fit for purpose. So we are going to keep and reuse all 4 of them. The structural engineer calculated and provided a design which took into account the stresses, pressures, and our requirements. This started with a layer 200mm thick of an MOT Type 1 construction aggregate, which is 40mm down to dust. This would be compacted, and then a 300mm layer of track ballast, which is 50mm to 32mm, would be laid on top of this and also compacted. Next would be concrete sleepers and rails, which will be fitted together in the normal fashion as on a standard rail line. Then the entire area would be fitted with 2 levels of 393 steel mesh for reinforcement, tied together, and then finally all would be encased in a C50 ready-mix concrete, which is about the same strength concrete you may find on structural beams on bridges. We have a plan. It's time to get started on the demolition of the existing track. On day 1, it felt like being lost in the wilderness. So we cleared the site of all vegetation and waste. This gave us a better understanding of the conditions of the site and enabled surveys to take place. First, we carried out a topographical survey, which measured the layout, boundaries, and levels of the land. Then, it was a BRE 365 test, which measures the soil's ability to absorb water. Last was an underground utility survey to identify and map the locations of buried utilities like pipes and cables beneath the ground. All track needed to be disconnected, lifted, and retained. In some areas, we needed to dig them out of soil, and in others, break away tarmac and concrete. We segregated and stockpiled all material to be processed and reused. First, we disconnect the plates joining the rails together called fish plates. Using a keying hammer, we remove some of the spring clips called pandoral clips. This separates the rail from the sleepers where need be. We have 2 types of rail in the yard. This is flat bottom, which is attached to the sleepers using the pandoral clips on either side. We then wrap chains around and use machines to lift each section, which is referred to as a panel. The panels we are lifting can be up to 18 meters long. Each rail weighs 1 ton and each concrete sleeper roughly 300 kilos. In a siding like ours, there'll be 24 concrete sleepers, so an entire 18-meter section will weigh just under 10 tons. We stockpile the panels out of the way to create space for the next stage of work and assess the quality of the track, which has telltale signs that it could be from the 1950s and 60s. When examining the rail, you look for signs of corrosion and wear, because dependent on traffic, track can wear out. The flat bottom rail should measure 158mm from top to bottom, and the bullhead 145mm. The tolerance on both is 6mm. Any more on the rails will be going to rail heaven, the scrapyard. Using the information from the topographical survey, we used the bulldozer to grade and create the new level for the base layer of the track build-up. With the levels in place, it was time for the 200mm thick layer of Type 1 MOT. This was distributed evenly and then whackered. The whacking process uses a vibrating plate to compact and create a solid base for foundations to be built upon. It's 300mm of track ballast next laid directly on top of the Type 1. This was distributed evenly and then compacted in the same way as the layer below. To save on costs, we're trying to use every inch of rail. We have some bullhead rail which has been disconnected from rotten timber sleepers. We're assembling a panel using the bullhead rail and sleepers which have been disconnected from the panel which sits beneath it. As our track will be encased in concrete, we've decided that sleepers will be placed at twice the normal spacing as out on the main line, because their only job is to keep the distance between the rails called the gauge and support until the concrete is poured. Fitting bullhead rail is a different process than flat bottom. You need to drop the rail in and push it to one side of the U-shaped fitting on the sleeper called a chair. Then you insert a fitting called the key into the other side of the rail and knock it in with a hammer so it's locked. We now drop the ready-made panels in place and roughly line them up. For our train to move between the two lines, we need a switching point made up of two parts, one on either rail which are connected to each other. Our switching points are made up of two panels, one with blades which move called a switch panel and the other a crossing panel. These are also dropped into place and roughly lined up. Our switch points are in a poor state and need repair, so we start by replacing the wooden sleepers. Then we change some of the base plates, which are the flat panels the moving rails slide on top of. The bolts which attach the chairs to the sleepers are called chair screws. The yellow plugs are called ferrules. This acts to facilitate the chair screwing through the chair to the sleeper without having metal on metal contact. This will be the only area of the train line which will not be concreted, as it has working parts we need to access for maintenance. To connect the rails, we first line them up with a jack called a duff jack. Then use fish plates and bolts. The holes on the fish plates are 27mm, the bolts 25mm, and the holes on the rails 30mm. The bolts are then tightened using a power wrench. When bullhead and flat bottom rail meet, a special junction plate is used to join the sections together. As we're using only rail which we have, at some points the rails on the panels do not finish flush. As we want the fish plates at exactly the same points, we need to square off the joints. We do this using a rail saw with a locking arm and 14-inch blade. We then drill 30mm holes using a rail drill so the fish plates can be attached.
Bolts around the wrong way.
Hello, put them inside.
We wanted the buffer stops to be squared off, which meant we cut in closure rails, which are basically lengths to fill in any gaps in track. The first layer of track ballast we compacted earlier is called the bottom ballast. Now, in a standard rail setup on the main line, the track is laid on top of the bottom ballast 25mm lower than the final height. Then the track is raised, ballast is pushed beneath the sleepers to build it up to the correct height, and then the remaining track ballast sits up to the top of the sleepers. As our setup is different and we need the gap between the sleepers, called the bed, free for reinforcement, in some areas we need to remove additional track ballast, and in others add more so we have enough to build up the levels. When adjusting the track, the focus is on height and then alignment. 3D surveying equipment is used for the final adjustments referred to in rail as lining and leveling. The process is to set up one rail correctly and then use the cross level, which looks a lot like a spirit level, to match the heights exactly. In areas where the track needs to be raised, a number of duff jacks are put in place to prepare for the next step called tamping. The tolerance and margin for error in height is 30mm, which is 10mm higher or 20mm below. Alignment-wise, the tolerance is 30mm, which is 15mm either side. Cue the beast. This is a custom excavator with rail wheels known as a road rail vehicle. It has a specialist hydraulic attachment called a tamper, which pushes the track ballast beneath the sleepers. Once the track ballast is beneath the sleepers, the duff jacks can be removed. To extend the life of our track, we're using profile grinders. This is the process of removing the sharp edge from the rail to create a curved edge. This allows the wheels from the train to travel smoothly without obstructions. Dependent on rail traffic, this can increase the life of our track by up to 25 years. It's time to prepare for concrete. We lay membrane between the sleepers as a damp-proof barrier to prevent moisture rising from the ground into the concrete slab, which will help maintain the concrete strength. It also helps separate the concrete from the subbase, allowing for better expansion and contraction without adhesion issues. On top of this, we lay 2 layers of 393 steel mesh for reinforcement. Shuttering, which is basically a temporary mold for wet concrete to cure, is created using 4x2 timber and shuttering ply. The carpenters create an outdoor workshop area and mass produce the main sections. The smaller intricate and finishing parts are made in situ. The concrete will be extremely heavy when poured, so it's essential the shuttering is supported and braced well. This is done using a mix of timber and reinforced bar being driven into the ground with props wedged in place to support. When the shuttering is complete, the lower levels of mesh are raised on small blocks. The mesh does not touch the bottom as it's designed to be placed mid-depth, as that is the area which faces the most stress and is prone to cracking. The top layer can then be installed and both are tied together. It's time for concrete. This is going to be a C50 strength mix, which will be level with the rails on the outside and 50mm lower on the inside between them. The concrete lorry cannot get close enough to the area to discharge directly, so we use a line pump. A vibrating concrete poker is used to remove the trapped air bubbles within the wet concrete to help increase the consistency by compacting the concrete evenly throughout. The vibrations basically allow air to rise to the surface, leaving behind denser concrete. We're pouring the concrete in 6-meter sections. This will happen in different locations up and down the line dependent on the progress of work. The plan is to pour one, miss one, pour one, miss one, and so on. Then fill in the gaps which were missed. We do this to create expansion joints between the slabs, which are controlled breaks to accommodate movement. We fit fiberboard expansion joint strips. This allows the concrete to expand and contract freely, managing stress within the structure. Once the concrete is cured, we strike out the shuttering, which basically means it's removed. We then clean the rails of any excess concrete with a wire brush, remove any loose debris, and give it a general tidy up. The unconcreted area around the points will have high foot traffic, as shunters who operate the points and maintenance teams require constant access. We need to create a safe walkway, free of any trip hazards, which we're going to do using 38mm sheets of waffle board. First, we need to build up the level and create a void. We do this by fitting sleepers to the existing sleepers. Then we attach the sheets of waffle board with clips to ensure they are secure, but can be lifted easily for access. All the billing and paperwork is beginning to come in, and I am doing my sums. Now, when I tally up all the drawings surveyors, engineers, labor, materials, concrete, and plant hire, the installation of our new track has cost us just over £750,000 plus VAT, which is not what we budgeted for. The track inspection is carried out by an engineer called a handback specialist. It's a visual inspection to look for defects, then measuring the distance between and the cross level of the rails. The angle of the corners is checked to ensure they're not too sharp and within tolerance, as this is an area where derailments can happen. As our depot is only slow moving traffic, this is not much of an issue. Finally, a walk-in measuring wheel is used to register the length of the track. It's been 28 days. The concrete has cured. It has been inspected by the track installer, who's given us sign off and given us the go ahead that we can actually test it with a 130-ton locomotive, which GB Rail Freight have agreed to send. Now, while I'm excited, I'm slightly apprehensive because anything can happen in a real life situation. The concrete can begin to break away. There could be an air pocket here, which collapses under the weight of the train and it derails. Today, we learned how to install a rail line and how much it costs. And in part 2 of this video, we're gonna see if it actually works. I'm Daniel, this is Ashville, and thank you for watching.